Hi guys. So I'm going to present today on the role of circular economy, energy and environmental systems in decarbonisation of hard to abate sectors. So hard to abate sectors are things that are difficult to decarbonise. So agriculture and aviation and fertiliser. So I work in the MaREI Centre. I've been the director of the MaREI Centre for 10 years, and we have this whole systems approach. So I think we've graduated 300 PhDs on these topics. And the idea is to get microbiologists, civil engineers, ecologists to look at a problem from different perspectives. So we have a lot of collaboration, a lot of multidisciplinarity. So we look at the energy transition, we look at offshore, we look at climate science, and we've some lovely work going on that I'm not overly involved in. For example, we've tracked the flight path of puffins and of gannets. We've tracked dolphins diving, seals diving. We have a plane that's going around the island looking at different whales and dolphins and different life forms in our oceans. And the idea behind it all, I suppose, is that if we put something in the ocean, it's not in the flight path of a puffin or a gannet, or if we have an underwater wave device or tidal device, that we're not going to find seals and dolphins immersed. So we have a lot of knowledge and a lot of data, and we work together. So I'm the director of that centre. I'm also the professor of civil engineering, and I spend a bit of time in Cornell and Paris. So we do a lot of collaboration and internationalization, and we try to work with the best centres we can. So one of my PhDs is going off to MIT over the summer. So we're trying to ensure that what we do is state of the art and that it's calibrated and we're doing the right things. And these are some of the people in the centre. We typically meet up once a year. At the moment, I think we have 89 PhD students due to finish this year. So we have a lot of research and a lot of stories. If I start off with decarbonisation and looking at electricity, because typically when people think of renewable energy, they imagine a wind turbine or a photovoltaic array to get electricity from the sun. One thing that we're quite unique in is we are an island, and we have what is called an islanded grid. And an islanded grid is difficult as compared to being Germany and you're connected into Denmark and France and maybe to Norway. We're not connected. I'm not an electrical engineer. There are electrical engineers in the centre, but we have this definition which is called system non-synchronous penetration. What it really means is how much of your electricity are you getting from wind at any one time, as opposed to a coal plant or a gas plant. So the wind sort of is variable and it's up and down and it's on and off. And Ireland has a world record in running a grid at 75% system non-synchronous penetration. So EirGrid, who at the moment are trying to rebuild our electricity grid, have managed to create our electricity system into one of the most advanced in the world in terms of dealing with offshore. But what that entails, for example, again, we've built the world's largest flywheel. So we spent 150 million on a 100-ton. It's called a synchronous condenser in Money Point. And the sole function of this is to provide stability to the electricity grid. It provides inertia. So the reason we built this was we have so many wind turbines which are causing fluctuations in frequency in the electricity system. So I suppose what I'm saying is that it's very, very difficult to be an islanded grid. And all of that was required when we are at about 40% renewable electricity. The target for 2030 is 80% renewable electricity. So it will be probably twice as hard to do what we're expected to do in 2030 than what we're already doing now, which is very, very difficult. I'm doing a little bit of work in America, and Texas is an islanded grid because they just didn't interconnect. And you've all heard of blackouts in Texas. So this is all about not having blackouts, not having volatility and voltage through the electric wires. So it's very challenging, and it's going to be a lot more challenging. And we have plans. These are offshore wind turbines. I think we're the first offshore wind farm of Wexford back towards 2001, 2002. We didn't go much further since then, but this is an auction pipeline. So this is offshore renewable energy supply scheme. And we have a pipeline to auction 17 gigawatts of offshore wind by 2030. And we've never used more than 6. So we're going to provide almost 3 times as much electricity we need in offshore, which is very challenging. And we also have a plan for 9 gigawatts of onshore wind and 9 gigawatts of PV. So producing way more electricity than we need. And there's a reason for that, which I'll talk about. But there is this concept of electrifying everything we do. And when you look at offshore wind, like what we're looking at is a 15 megawatt turbine, which is 330 meters from top to tip, which is the size of the Eiffel Tower. And if we put 7 gigawatts in the water by 2030, which is our target, that's 467 Eiffel Tower sized structures in the water by 2030. So that's the scale of the easy to decarbonize sector. And one of my graduates, I'm a civil engineer, one of my graduates in 2012, his work at the moment is a method statement. So what do you do to get it in the water? So we need to redesign our ports. We need this sort of a big circle. The ship comes in, picks up a little bit of the turbine, another bit of the turbine, goes around, goes out to sea, and then a boat goes with it, and we try to put it in the water. So it's very much a civil engineering problem set. How do you do it? And we've huge issues off the west coast of Ireland because you probably get 70 days a year when you can do it. So we're looking at wet storage in the Foynes, and that's getting all these turbines on barges sitting there waiting for some good weather, and then they all go out at the same time and try to get these Eiffel Towers up. I mean, I think it's probably challenging, and we'd probably feel very proud if you got 1 Eiffel Tower up, but we're meant to get 467 Eiffel Towers up in the water by 2030. I think there's a belief now it'll probably be 2032, and one of the issues is planning, and we have a very slow planning process. So people can say, I don't want that, and then it slows things down. But at the moment, we've already auctioned, I think this is gone. So we've auctioned through 3 gigawatts. So people have permission to put up the 3 gigawatts, but there is a planning process going off. So these are the proposed wind farms around the country. The first ones are off Dublin. And the reason they're off Dublin is Dublin has a demand for about 1.5 gigawatts of electricity. So we'll build these wind farms. This is a 3 gigawatt all along here, and we'll supply it into Dublin, into data centres, and Dublin will have renewable electricity. The next phase is down here. This is our harbour in Cork. And these are what we call designated marine area plans. So they've been surveyed, we've looked at them, we've looked at the depth, and we're going to put this 900 megawatt down around off Waterford. And there's a strong chance that it'll come in Cork. And these two I'm very interested in. These are 2, so this gets us to 7. But these guys are orange, and we call them non-grid. And it means that they won't go into the electricity grid. And the reason is, so Cork has a demand of 0.3 of a gigawatt. So we're going to build in the next phase about 900 megawatts. So that's about 3 times what Cork needs. The electric wires will take about 300 to Dublin. So when we start putting all these wind turbines off Cork, it's too much electricity for Cork and for the power lines. So these two guys are meant to be, they're not going into the transmission grid. They're going to stay in Cork. And we can do things in Cork. So what will we do in Cork to use all this electricity? And there's a perspective, we could have an energy park. We could have data centers, or we could make hydrogen, or we can do other things. One of the concerns is that 7 gigawatts will cost about 25 billion for the offshore winds. For the 467 Eiffel Towers come at a cost of about 25 billion to build, which is about 25,000 per home. But that's what renewable electricity looks like in Ireland. That is the challenge. And there's a viewpoint that will electrify everything based on offshore wind and onshore wind and PV. So there's people who believe everything will be electrified, and I'm not one of them. There's a plan that we have 1 million electric cars by 2030. Now, we're not buying enough, but everyone should drive an electric car, and they plug it into their house, and they have PV, and there's offshore wind. So I'm saying 30,000 per house, roughly. And then we should all deep retrofit. So we put underfloor heating in, we put insulation in the walls. An average home will cost 60,000. This is a government projection. And they want 1 million homes to be deep retrofitted. So you typically dig up your floor, underfloor heating, insulation, probably outside the wall. We're doing work that insulation in the wall is probably not good in terms of cracking the wall and dampness. So basically you put a hood over your house like a tea cozy, you dig up your floors, underfloor heating, no rads, heat exchanger, 60,000, 4 months in a hotel, come back into your house. So that's electrifying your house. And we have a new building standard that comes in that all houses need to be zero energy, so that you produce all your energy for your house on your house. So you'll have PV, you might have a wind turbine, but you should not be affected by a storm because your house is producing all the electricity that you need. I was saying to Finbar there, I met before, and I was up in Sweden, and they built this lovely, maybe 15-story building. They built it in panels that would create electricity, and it was fantastic. But then somebody built across the road and put them in the shade, and it wasn't working anymore. So this is the easy bit, and I think that's important. This is the easy bit, and it's going to cost, I don't know, about, well, the deep retrofit is 60 grand, your electric car is 30 grand. I'm reckoning about 120,000 per home to sort of do that easy bit. Well, then the problems we have is electricity is 20% of energy. If we get to 80% renewable electricity, that's 80% of 20%, it's 16% of energy. And that ignores the fact that the cattle are belching. And we have open slurry storage. And we have about 8 million cattle in the country. And typically, a cow is equivalent to about 20 people in terms of their footprint, because they belch methane. And methane is 28 times more warming than CO2. So agriculture is responsible for 38% of our greenhouse gas. So doing all those turbines will do nothing to the cow in the field that is belching, putting fertilizer on the soil, and having open slurry tanks. We also have a problem of haulage. These will not run on batteries. Well, they might run for 300 kilometers in batteries, but planes will not run on batteries, ships won't run on batteries, and a lot of haulage won't run on batteries. So we need a liquid, and it has to be a renewable liquid. And then we have cement. Cement is a huge producer of CO2. Steel is a huge producer of CO2. So how do we get to climate neutrality when all of that work will get us a small bit, and we're still of the cattle and the cement and the steel and the ships and the planes? It's a huge task. And I suppose that's something I'm trying to address. So the challenges of net zero or climate neutrality are cattle. Cattle can't belch anymore. We can't have open slurry tanks. And then we start looking at things like hydrogen. I mean, at the moment, we produce 1 million tons of hydrogen, and they're required in lots of products. And that's fossil hydrogen. We make hydrogen from natural gas. A lot of my work is to do with the hydrogen molecules. That's H2. But natural gas is CH4. So everything with a H tends to come from natural gas. And what's interesting is natural gas produces twice as much energy as the electricity grid. So if you look at electricity on planet Earth, double that, and that's what natural gas does in terms of energy. So if you think of the combined cycle gas turbines in the harbour, they're natural gas. We burn natural gas in our homes. So what do we do to get rid of natural gas? Or how do we make renewable natural gas? And then the problem is, besides energy, that natural gas is used to make hydrogen, 100 million tons a year, methanol. Now, methanol is the world's second most produced chemical, and it's a precursor to plastics and paints and cosmetics. So if you look at everything you have around you, it's probably oil or gas in some form or other. So we produce 110 million tons of methanol. So we can see methanol is methane with an oxygen molecule. So methane is CH4, stick in an oxygen and you've methanol. You don't drink methanol. Just by the way, there's a lot of people struggling in Southeast Asia being fed methanol. Methanol is a bad fermentation of alcohol. You get methanol and it makes you blind and it kills you. So you don't drink methanol. And it doesn't burn with a flame, which is quite frightening. I've seen a methanol car go on fire. There's no flame, but people are burning. So it's seen as the transport fuel of shipping. But the problem is if it goes on fire, we don't know it's on fire. So it's challenging. Ammonia, again, you've got your H from natural gas, and now you've got N, and we get that N from the atmosphere because nitrogen is 80% air. So we make ammonia from natural gas, and ammonia is fertilizer. So when we put fertilizer on the soil, we're actually putting natural gas on the soil. And they all have to be decarbonized, and they're the difficult ones. And then we've jet fuel, and then we've shipping, and they're responsible for 5% of CO2 emissions, but they also have more warming. So a jet in the sky has a contrail, particulate matter, and all of that causes warming. So these are the hard to abate sectors, and I would include cement and steel production. These are the people I work with on a daily basis. So all of the work I'm talking about is from this group, these good colleagues of mine, Arkesman Bose, David Wall, Richie O'Shea, and I think 7 PhDs graduated from this group this summer. We all work in these problems. So the data I'm giving you is from all of my good colleagues who work together. And this is our menu. This is what we every one of that group works on this map, and we all try to figure out where we're working. So I'll start slowly. So we start down here in agriculture. We have a lot of work in agriculture and anaerobic digestion. And what's interesting is the war in Ukraine became a huge problem for Europe, besides death and bombs, but in terms of natural gas. So Russia produces most of our natural gas. 100% of Austrian gas comes from Russia. Russia shut the valve. Austria has no gas. So you've no gas, you've no fertilizer, you've no whiskey, you've no beer. So if you think of Irish distillers, they use 60 megawatts of natural gas. If you think of Diageo, if you think of cheese, if you think of infant, it's all natural gas. So all of a sudden, if our valve is shut, we can't do much without that natural gas. So Repower EU is a document where Europe is looking at repowering. And this came about because of security of supply. It happened very quickly. 10% of natural gas has to be replaced by 2030 with biomethane. And Ireland had to do the same. So we have a climate action plan, which says that 10% of our natural gas has to come from biomethane by 2030. And that's, in Ireland, 3.75 terawatt hours. It will be probably 300 very, very large anaerobic digesters that will take in slurries. And I suppose the benefit of this is that if you have an open slurry tank, methane goes to the atmosphere. It's 28 times more pollutant than CO2. In this, we capture that methane. It doesn't go to the atmosphere. And we burn it and it becomes CO2. And CO2 is 28 times less warming than methane. So we use it as a fuel. And converting it to CO2 is 28 times better than not converting it to CO2. It's a biological process. A lot of my work is, I suppose I would consider myself a biological engineer at this stage. We start off, for example, with grass. We convert it to a liquid. Then it becomes lovely volatile fatty acids. And then we convert it to methane and carbon dioxide. It's typically 60% methane and 40% carbon dioxide. And it happens very easy. If you cut grass and put it in a barrel and cover it, if you went back a week later, it's this sort of sweet liquid. That's all the volatile fatty acids. And if you left it long enough, it would explode because it would have methane. So the idea is to do this in a controlled process and put it into the gas grid. So we'll probably spend about, I'd say, $1 billion on that by 2030. And the idea is that it would be slurries and food waste and stuff that isn't very pleasant. So I led the International Energy Agency Biogas Task for 6 years, and we produced lots of documents, and they're all available for free online. So if you click on this, you'll get technical reports. If you click on this, you'll get case studies. I just wanted to pick on these 4, so I'll do them one by one. So what we're looking at here is that an open slurry tank, if you ever see an open slurry tank, that's methane going to the atmosphere. And if you cover that tank, the methane isn't going to the atmosphere. And if you put it into a bus or a coach and you run the bus or coach, that will emit CO2, which is 28 times better than emitting methane. So the California Air Resources Board awarded a carbon intensity of minus 255 grams CO2 per megajoule from dairy waste to a bus or a truck. So it means the more buses you have running on slurry, the better the environment is. And that's an important one because some people think, oh, it's methane is bad, but the bus will convert it to CO2. And we did a lot of studies on biogas plants and slippage, but in essence, by burning methane that would have gone to the atmosphere in a bus, it's better for the environment. So the more buses and the more digesters, the better you are. Another one, we spend a bit of time in the Po Valley, so it's the northeast of Italy, and it's called Biogas Done Right. And they're trying to decarbonize agriculture. So what they've been looking at is when you break the soil by ploughing it, you give off N2O, and N2O is 280 times more warming than CO2. So we've 3 greenhouse gases. CO2 is 1, it's the best. Methane is 28 times worse, but N2O is 298 times. So when we plow the soil or put on fertilizer, we give off N2O. So they never plow the soil. It's called no-till. And they actually grow a crop under maize. So maize is grown for cattle, and then under the maize there's a grass. And the grass goes into the digester with slurry, and you digest it, and you can put biomethane into the grid, but you've also got a biofertilizer. So the biofertilizer goes back in the soil. And you might remember ammonia is the source of fertilizer, and that's natural gas. So you've got rid of ammonia. So you're not putting natural gas on the soil, you're putting biofertilizer from the biogas plant, you're producing biomethane, and you also produce CO2, which is also quite important. So their viewpoint is they've greatly reduced the carbon footprint of their agriculture. They've no N2O, no fertilizer, 2 crops, digest all that slurry, no methane going to the atmosphere, and they've gas in the gas grid. That wasn't there before. This is another one I like. REPowerEU has decided that by 2030, 25% of all agricultural land will be organic. And organic means no fertilizer, no pesticides. So this is a farm we visited up in Denmark. No weed killers, so they have little trolleys, people lie in them, the tractor pulls them along, they pick weeds. All of the organic material goes into a digester, and that makes a fertilizer. So if you don't have a fertilizer, your yields go down to about 10%, but their fertilizer comes from digesting all their byproducts, putting it on the land, and they're certified as a greenhouse gas negative farm. So per litre of milk. So there's no fertilizer, there is no emission from open slurry tanks, there's no pesticides, and Europe is saying 25% of agricultural land will be organic by 2030. And that'll be a huge impact in Ireland. But you're greatly reducing the carbon footprint of agriculture. You probably have less produce, but hopefully a higher value. Another one we're looking at is CO2. CO2 is a product. Denmark, for example, sells 50,000 tons of CO2 per year. We're probably similar. When Brexit happened in the UK, you might remember, or you might not, they couldn't slaughter pigs. It was a big issue. I don't know if anyone remembers that. The reason they couldn't slaughter pigs was CO2 comes from fertilizer production. So if you have a facility converting natural gas, CH4, into ammonia, NH3, the CO2 goes off. So you produce ammonia, CO2 is a byproduct, and CO2 is put into a slaughterhouse to make animals drowsy. So you put them into a room full of CO2, and then you shoot them, and then you cut them up and you eat them. We need CO2 for soft drinks, Lucozade, beer, dry ice, lasers, welding. So this is biogenic CO2. So this facility puts the methane in the gas grid and they sell the biogenic CO2. And in Canada, there's a thing called bullfrog. You get a stamp on your drink saying this is a carbon neutral drink. So the CO2 bubbles in here probably come from a fertilizer facility. So someone split natural gas, grabbed in out of the atmosphere, CO2 went off and they put it into my drink. Where it could be from slurry, which would be a lot nicer. So there's a market for CO2. So I suppose our anaerobic digester is reducing emissions from agriculture, producing a fertilizer, producing CO2, and also producing biomethane for the gas grid. Now, I understand at the moment in the UK, CO2 from anaerobic digesters is used for offsetting. So Virgin Atlantic pay people in the UK 100 euros a tonne. So the CO2 that comes out of that is put underground. And Virgin Atlantic paid them 100 euros a tonne. So when you're buying a carbon credit for your flight, it's an anaerobic digester in the UK that puts the CO2 underground. And it's expected that by 2030, they'll make more money from the CO2 than they will from the methane. And I'll come back to renewable hydrocarbons in a minute, but CO2 will have a lot more value in the future. Another thing we've been looking at, we've been working in Dingle with the Dingle Hub. It's been a lovely project, loads of community engagement. We've been on there for around 10 years. But we went down about 10 years ago, we spoke to Dingle about the environment. And it's been a fabulous journey. If you go to Dingle now, there's buses going every half hour all around the peninsula. Most of them are now electric buses. There's a co-op of farmers led by Dinny, and they all have PV and they all have apps. So we're looking at decarbonising Dingle as a rural peninsula. But what we've said to them is, what do you need? And they came back to us and they said, well, our cattle go into the mainland and they're slaughtered, and we don't know what is Dingle cow and what is a Cork cow. So they want an abattoir. And they tried to have an abattoir, but they were priced out of the market in the treatment of byproducts, because we have more or less a monopoly in the slaughter industry in Ireland. I won't go political, but so if they had an anaerobic digester, they could slaughter their animals and the byproducts would go into their digester. So they could sell their beef as Dingle beef and charge €2 extra. Dingle beef tastes salty from the Dingle Peninsula, our food, slow food, our abattoir. Another thing is they spend $1 million a year sending their food waste to Waterford to be composted. It could go in there. So you're saving $1 million a year. You've got the slow food movement. When we went to Dingle the first time, there was Tralee Bay oysters. So they grow oysters and they feed them microalgae. So what we've developed, and this is Arkisman Bose, one of my good colleagues, if we send biogas up through a tower, which is methane and carbon dioxide, we also send microalgae up the tower, we get loads of microalgae. So the microalgae eat the CO2 and you have pure methane. And the microalgae is a vegan food product. And we use it at home. We make smoothies from microalgae. It's about €4 for 40 grams. That's 10,000 euros a tonne for microalgae. So the idea is we'll grow microalgae, they'll sell it at loads of money, they'll have their abattoir, they'll have the slow food movement, and that's a digester in a circular economy designed by the community, what the community wants. It's a small scale digester, but they want to use the methane to run their tractors. So their tractors will run on biomethane from the slaughter industry, they'll have a biofertilizer, they'll have microalgae, and they're all happy with this. And we're looking at funding at the moment of 1.5 million to start this process. I wrote this piece of work for the International Energy Agency. We launched it last January. It was a lot of work. It was a labor of love. I really enjoyed it. And this is where biogenic CO2 becomes very important. So if we look at the hard to abate sectors, it's hydrogen, it's methane, it's methanol, it's ammonia, it's jet fuel. So in 2035, when we have all these offshore wind turbines and all our electricity is carbon neutral, and we've all spent 60,000 euros on our houses and we're all driving electric cars, the next step is fertilizer, farming, getting on the plane. So all of us will get on a plane and we'll fly to Spain or Australia. That's probably a bigger carbon footprint than the whole year. So we have to deal with jet fuel, or else we get on a boat, and that boat is going to have lots of oil which we'll burn. So we need to look at that. So I suppose a lot of our work is 2035 onwards. So if I start with this one, again, I'm back to offshore wind. I'm now down in Cork. I'm now looking at these two guys. These are 2 gigawatts of offshore wind that will not go into the electricity grid. So we've had a project involving lots of utilities looking at Cork Harbour. We expect 1 gigawatt to come in. So our options are data centres. We'll build data centres in Cork. Or we can plug in ships. So the ships that come into the Ring of Skiddy, we've got cruise ships, they're burning bulk fuel and there's horrible particulates going up. So they go on electricity, they plug in, and the air is far, far better. I was down in New Zealand. I had a big carbon footprint going down. I was there for 2 weeks at work. And the biggest source of air pollution in Canterbury was cruise ships. So it's the worst possible fuel goes in a ship. So you have all this horrible particulates going out, you get subadiabatic inversions, people have asthma, they go to hospital. So they don't want that horrible fuel. And if you look at the ships coming into Ring of Skiddy, they're massive. They probably have power production similar to Cork City, and it's horrible burnt fuel. So the idea is we get batteries for them. What we can also do is, there was an ammonia facility in the harbour. It's still there, 200-acre site. When we had natural gas, back in the 80s, we built an ammonia facility, and that was fertilizer. So what we could do, we could convert the electricity to hydrogen, react it with nitrogen, and make ammonia again. The site is there, it's vacant. There's a rail line behind it. We can make fertilizer, take it away in a train, and that would improve agriculture. We could make methanol, and methanol is a precursor to formaldehyde and all green chemistry. Or methanol can be used for shipping. So we've lots of options, and that's what we've been looking at. A problem with hydrogen is that it's very voluminous, and people consider hydrogen as a sort of a battery, that you have loads of wind. So the 17 gigawatts is turning. We're using 6. So there's 11 we haven't used. So what we would do is we would convert it into hydrogen, and we'd have loads of hydrogen. And it's seen as a battery. And the idea is that we would put that hydrogen off here in the old gas fields. And they've been looking at the old gas fields for, number 1, storing carbon dioxide, number 2, storing hydrogen, number 3, storing methane. But we could store hydrogen in the old gas fields. We could have 20 days storage. And there's a thing called Dunkelflaute, and that means no wind. And it happens every year in Ireland. We had 2 weeks of Dunkelflaute last November. There was no wind. Wind provided about 6% of electricity, 94 came from gas. So the idea would be, in that period of Dunkelflaute, we fill it with hydrogen, and the hydrogen comes into the combined cycle gas turbines, and it's green electricity from hydrogen in a chemical battery. A problem is that it's very expensive. And the viewpoint of the grid is that, well, what's worse is that we have power outages. And then Amazon goes down and Facebook goes down and they leave the country. And so they see that investment not in terms of cost of electricity, but it provides stability for the other 365 days. So when we're looking at hydrogen, I suppose we would look at it as a molecule. If we want to make fertilizer or methanol or ammonia, we need the hydrogen molecule. And that is why we're going to overproduce electricity, for the hydrogen molecule, which is ubiquitous. It's in everything we do when we get beyond electrifying our cars and our houses. We're looking then at where to put the electrolyzer. One thing we're looking at, so we have this 300-meter high turbine out in the water, and we have a cable that comes ashore. This is a HVDC cable. It's a high voltage DC cable. For example, there's a new factory in Oslo that was built for us. So we're having a connector from France to Ireland. It's a 0.75 gigawatt. It's going to cost 2 billion. They're building a brand new factory in Oslo to make the cable, to give it to us, to connect us with France. Now that's 0.75. We're going to have 17. So we'll need probably 20 of those factories to make cables. So this HVDC cable is very, very expensive. You have to wait a long time to get it. Someone has to make a factory to make it. They bring it over by ship and you start laying it. The idea is that a lot of these turbines off the west coast of Ireland will be 60 kilometres out. So you'll bring the electricity ashore into a substation and then make hydrogen on the shore. But you can also make hydrogen on the turbine. So you can be out at sea. There's the Eiffel Tower, 60 kilometres off the coast. You have an electrolyzer. You'd have a desalination unit and you make hydrogen. And a ship comes up next to it and you plug in the hydrogen. Or you could have a Haber-Bosch process. You could make ammonia. So in effect, we could have these massive factories out in the ocean and ships pull up next to it like a service station and they take away the ammonia, or they take away the hydrogen, or they take away the methanol. So it's sort of exciting what we could be doing in 2035 or 2040. Hydrogen is very expensive. So what we were looking at is how would you make it cheap? So you have your offshore wind turbines, 17 gigawatts. We only require 6. So when there's a huge demand for electricity, the first auction was about 8 cents a kilowatt hour. But then if we've loads of wind and we're all asleep and nobody wants it, the value of electricity falls. So there's the day ahead market. So what we're looking at is somebody would set up an auction system. They'd buy electricity at 4 cents a kilowatt hour, which would probably be in the middle of the night when we're all asleep and it's very windy and nobody wants the electricity. And we would convert it to hydrogen at 12 cents a kilowatt hour. Now, 12 cents a kilowatt hour is about 1.2 euros per litre of diesel. So if I say diesel is 170, that's 17 cents a kilowatt hour. So even though this is expensive, it's cheaper than diesel. So there is a viewpoint that we use hydrogen as a fuel, with a fuel cell. And it mightn't be that expensive. It's very expensive for electricity because if you convert that back to electricity at 11 cents, you'll probably get at best 50% efficiency. So it's 22 cents a kilowatt hour of electricity, produce some electricity at 4 cents. So if you have electricity and you make hydrogen and you come back to electricity, you've increased the cost by a factor of 5. And then if you're storing it in an old gas field, you'd compress it, put it into the gas field and bring it back. So wind to hydrogen to electricity is really expensive. But hydrogen by itself is not bad for fuel, but it will be very, very expensive. We have this idea of converting it to methane. And if we convert it to methane, we could put it in the gas grid. It would be a lot easier. We wouldn't have to go into the old gas field of Cork. We could just put it straight into the existing pipes. And those pipes run all around the country. And this is a simple process. Again, I suppose I'm a biological engineer. This is the anaerobic digestion process. And these little guys are hydrogenic trophic methanogenic RK. They're here since the birth of the planet. They've been doing this forever. If you feed them hydrogen and carbon dioxide, they make methane. And it's exothermic. So these guys are going to work very happily themselves. So we went into the lab and we fed hydrogen and carbon dioxide to a broth and we got pure methane. And then we developed a process where we added hydrogen, so from offshore wind, CO2 from our biomethane plant. And we need a process because hydrogen isn't very soluble. It needs to be under pressure. But we developed this system that converts hydrogen and carbon dioxide to methane. And this is it in our lab. We spent about 350,000 on this, but it works. So we have the first reactor, all the gases go into solution, second reactor, third reactor, and we're getting 97% methane. So we start with carbon dioxide, hydrogen from offshore wind, and we're making methane. So we call that X equal to 2. X is equal to 1 is hydrogen, X equal to 2 is methane, so we can put it in the gas grid. What we were then looking at is where would you have an electrolyzer in Cork? So we went to Cork Main Drainage. This is in Carrick-Brennan. It's a wastewater treatment plant. I was one of the design team back in 1992. And Cork Main Drainage is 426,000 people. It's an aeration basin. We pump in air. So our design principle was we'd stick an electrolyzer in Cork Main Drainage because not many people go to Cork Main Drainage. Has anyone else Anyone here walked across the wastewater treatment plant in Little Island? So we felt it would be good for planning. No one's been there. So you stick in your electrolyzer, you size it to provide oxygen. So your pumping has gone down by a factor of 5. You're not pumping air, you're only pumping oxygen. And we found that would be a 10 megawatt electrolyzer. What we do in Ireland is we curtail electricity because we're an island grid. 10% of electricity is always spilled. It's never produced at the right time. So if we had a 144 megawatt offshore farm, we could take 70 gigawatt hours per annum, which is 10 megawatts, without impacting anything. It's spilled anyway. So we'd spill it to Carragrenan, and that would allow us to upgrade the biogas. We have a sludge digester there. So we could run 300 trucks, 390 trucks. Some of them would be the biomethane, and the rest would be hydrogen. So we thought this was a case story. Stick the electrolyzer in the wastewater treatment plant, reduce the carbon footprint of the treatment plant to 40%, and you have 400 trucks powered from methane, from sludge and hydrogen. Denmark has 39% substitution of natural gas already. So in Denmark, you're not allowed to put slurry on the land. All slurry has to go into an anaerobic digester. All food waste goes into anaerobic digesters. And they have huge digesters. It's the model they've built. So you could have a 25-kilometer radius, and you could have about 800,000 tons a day of food waste, slaughter waste, slurry, and they put it all into the gas grid. So the reason they did it was they had eutrophication. And they decided back in 2010, all farmers would put their slurry in a tank. They subsidized the infrastructure. So at the moment, Denmark has roughly 40% on average over the year of their natural gas that comes from biomethane. And what they're now looking at is getting an electrolyzer to take hydrogen, the CO2 in the biogas, they'd convert to methane, and that would become 65%, purely by reacting hydrogen with CO2. So now they'll have 65% renewable gas in the gas grid from food waste and slurry, and now hydrogen. So we call it e-methane. It's methane that comes from electricity that's produced when we don't want it. So there will be overproduction of electricity to make hydrogen molecules. So that's one concept. And the joy of that, it goes into the gas grid, and the gas grid is there. So if you have a farm in Cork, you can put the molecules in Cork, and Dublin Bus can take it out. So it's easier than hydrogen. I go up to Linköping a lot. It's a little city in Sweden. They have a very good research group working on biomethane, and they had a slaughter facility, and they had a bus service. So back in around 1992, the last century, they decided that they had water quality problems and they had air quality problems. So the slaughter waste goes into a big anaerobic tank, and they pipe biomethane 4 kilometers, and they were running, I think, 200 buses. But now I was up there last year, and they're liquefying the biomethane, and they're running trucks 1,000 kilometers. Now, a battery won't take a bus 1,000 kilometers. So now you have slaughter waste taking that bus 1,000 kilometers on one fill. So what they do is they drop the temperature to -273. It's cryogenic. The methane goes into solution. It's a liquid, almost like diesel, and the truck goes 1,000 kilometers on one fill. And it's from slaughter waste and slurry and all these horrible things that we put on the land, and they go into our river, and 70% of our wells are contaminated. So they've got rid of that. So you do not put slurry on the land. We plough slaughter waste into arable land. You're not allowed to do that in Sweden. And Sweden doesn't have water quality problems. They have 40% renewable gas. They run their trucks on biomethane. So this is a circular economy system. And they have biofertilizer, and they have CO2. We've done a lot of work with distilleries. And this is quite interesting in that if you look at Diageo in Dublin, or if you look at Jemison in Middleton, and we've done work now on 10 distilleries. We've done work in Mexico, in Azerbaijan, in Sweden, and we've looked at how you decarbonize. So if you look at a distillery, what they do is they use natural gas to evaporate alcohol off stillage. So you get grains, you ferment them, you make a beer, and then you add in natural gas, you raise the temperature, and alcohol evaporates at about 700 degrees Celsius. But like my understanding is Middleton is around 60 megawatts of gas boilers. So really, we use an awful lot of gas to make whiskey. We use gas to make Guinness. We use gas to make milk formula. And it's hard to decarbonize because we don't have the power lines to go down to Middleton and convert it to pure electricity. One of the things we did a study and we looked at 21 decarbonisation pathways, but we couldn't get to zero carbon without anaerobic digestion of the byproducts. So we'd use biogas to replace natural gas. Or, that's called scope 1 emissions, or we could put the biomethane in the truck that goes out to the field and gets the grain and comes back in, and the biofertilizer would go on the land that grows the grain. So we could greatly reduce carbon either in the factory or in trucks going forwards or backwards or in biofertilizer. So we've done a lot of work on that, and we've greatly reduced the footprint of those facilities. And this brings us to X equal to 3, power to methanol. So this is something we'd love to see in the lower harbour. So you have offshore wind, RPV, and you make hydrogen. And that's renewable hydrogen. But if you want a hydrocarbon, which is petrol, diesel, jet fuel, you need green carbon as well. You can't take carbon from a coal plant. That's not allowed because that extends the life of fossil fuel. So the distillery in the lower harbour is 50,000 tonnes of CO2 from fermentation. If we build a biogas plant and replace natural gas, then the stack is also biogenic CO2. If you want to go, no problem. I can see you're edging to go. Just go. So you have a renewable carbon, you have a renewable hydrogen, and you're making a renewable hydrocarbon. So this is methanol, and the ship industry wants methanol. At the moment, Maersk, there's a target for sustainable shipping fuel. They're traveling across the planet to make methanol. For example, Maersk have gone up to Denmark and they're making biomethanol. So methane is CH4, which is from your digesters. If you add some oxygen, so we get our oxygen from CO2, you'll make methanol. So Maersk is going to Denmark and converting biomethane into biomethanol and putting it in ships. And that's biomethanol. E-methanol is offshore wind, split water into hydrogen, reacted with biogenic CO2, and that's e-methanol. So the market for biomethanol and e-methanol is huge. Already methanol is 110 million tonnes. We have to make that green if we're going to have net zero. But also methanol is going to be used in shipping, which is going to be another 100 million tonnes. So there'll be a huge market for methanol, offshore wind, biogenic CO2. And methanol is the precursor to formaldehyde and all these chemicals that we take for granted. So this will be a big industry. And we're saying this could be in Cork, because Cork will have a gigawatt of private wire. And our challenge is, what do we do with it? Are we going to have a data centre? Are we going to make ammonia? Are we going to make methanol? Will we produce shipping fuel? So this is Maersk McKinney, and they're converting biogas to methanol, and they're using liquefied biomethane to run ships. And they have to do it. There is a standard for shipping, and there's a standard for aviation. They have to hit certain targets. One is 2025, another 2030. And the idea is by 2050, every ship is running on a renewable hydrocarbon. Every plane is running on a renewable hydrocarbon. So the hydrogen will come from offshore wind. It'll be split. The carbon needs to be carbon neutral carbon, if that makes sense. We cannot use a fossil fuel. This is a facility we visited in Quebec on the Lawrence River. This was an ethanol facility. So they made ethanol for transport. So it's the same as whiskey. You get grain, you mash it, you heat it up, you make a beer, you distill it. So ethanol is double the strength of whiskey. But their carbon footprint was higher than Brazil. So when we look at fuels, we have a carbon intensity, gram CO2 per megajoule. Theirs was higher than Brazil, so they lost their market to Brazil. So what they did is they brought in a biogas plant and they started digesting byproducts and anything else they could get, and they replaced natural gas. So no more natural gas. So that dropped their carbon footprint. Then what they decided to do is they brought in a 60 megawatt electrolyzer, and up there they have hydroelectricity. So the grid is very low carbon. And they split water and they made hydrogen, and they react the hydrogen with the biogenic CO2. So the CO2 that comes out the stack is carbon neutral because you burn biomethane, not natural gas. When you make a whiskey or an ethanol, you fermentation gases anyway. So they now have three products. They have ethanol, they have ethanol, e-methanol, with an M in front of it, and biomethane. And they reduce the carbon footprint. So the carbon intensity of the ethanol, number one, is reduced because there's no more natural gas. And number two, all the carbon is divided into three. Some goes to ethanol, some to methanol, and some to biomethane. So they now have a lower carbon footprint than Brazil, so they have a market. They have a market again. Without doing that, they'd no market, they were out of business. And Maersk are buying their methanol. So the shipping companies say, we'll take that. So again, this is a cascading circular economy type system, offshore wind, PV, and capturing everything. And this is their footprint. So this is ethanol, this is their biogas plant, and this is their electrolyzer. And it all fits on the one site. So we would think this could happen at any distillery. Any distillery there is, capture their CO2. And the alternative renewable carbon dioxide is direct air carbon capture. So you pull CO2 out of the atmosphere, it's 400 euros a ton. So they can produce this at 20 euros a ton. So the value of the profit potential for them is producing it at 20 euros a ton, and their competition with direct air carbon capture 400 euros a ton. So they can make a profit of 380 euros a ton on biogenic CO2. And this is 2035 onwards, because we will have to have renewable hydrocarbons for ships, renewable hydrocarbons for planes. So all of a sudden, biogenic CO2 is very, very, very valuable. And at the moment, in most of the distilleries in Ireland, it goes straight up. But it won't be going straight up in 2035 because we'll have to make renewable fuels. So this is a sort of a model we've been looking at. You have an ethanol plant or a whiskey distillery or anything in the food and beverage. Ireland's responsible for 15% of the world's infant formula. So if you have a baby in China and you make a bottle and you feed that baby, it's probably Irish. And it's got a higher value because they see us as green. But all of these processes, the byproducts can be digested. So we have this is an anaerobic digester in two phases. So we have the biogenic CO2 from the process. We have the CO2 from the biogas, offshore wind electrolyzer, and we can make methanol, or we can make ammonia, or we can make jet fuel. And that's the thing we're looking at, eSAF. And what we're then looking at is the effluent can make duckweed, and typically the byproducts of a distillery feed cattle. So we can make duckweed to feed the cattle from the byproduct of the anaerobic digester. So we have this, we call it e-fuel, biofuel, e-refinery, biorefinery. Everything comes together. Electricity, whiskey, cheese, biogenic CO2, anaerobic digestion. And this is a renewable fertilizer. So again, you have an electrolyzer, and we grab nitrogen out of the air. It's called the Haber-Bosch process. So you have to have renewable hydrogen from offshore wind, and then you just pull nitrogen out of the atmosphere and make fertilizer. And again, the world produces 430 million tons of CO2 from the byproduct of fertilizer. So we need green fertilizer. So this is a Siemens plant in Cardiff, and Oxford University are behind it. eSAF. So if you go down to the refinery in the Lower Harbour, this is what they do. They make all these things from oil. They crack them into natural gas, LPG, petroleum, gasoline. We can do this with hydrogen and CO2. So we can make all these products. But this is where we get SAF. It's C13 to C18, kerosene and diesel. We did a paper, which I found very interesting, was led by Nathan Gray, my PhD student, and we looked at aviation. And combustion of jet fuel is 2% of the world's CO2. So the jet fuel is responsible for 2% of all CO2. But the problem with jet fuel, it's 33,000 feet up. And when you see contrails and particulate matter, the warming of aviation is 60% from that. And it's about 45% from combustion of fuel. So if you replace jet fuel with sustainable aviation fuel, it's half the problem. You still have the contrails. Now they're talking about flying at different heights. So a contrail is bad. If you get lower down and there isn't a contrail, that's better. But if you get lower down, there's more turbulence. So it's a sort of a wicked problem. But either way, if you want to have net zero aviation, you'd have to make ESAF, which is direct air carbon capture, 400 euros a ton, hydrogen, mix them together. It's about 4 times more expensive than jet fuel, and that's half the problem. So then you would build direct air carbon capture for the quantity of other warming to pull that out of the atmosphere. So our thesis is flying will be ridiculously expensive in a world where it's net zero. It'll be ridiculously expensive. And just there are things happening. This is a cluster that we're involved with, including Middleton, Urban Oil, Gas Networks Ireland, the ESB, and it's down in the Lower Harbour. This is Urban Oil. So we're looking at 1 gigawatt of offshore wind. We have loads of batteries. They're going to produce green hydrogen. They're going to make hydrogenated vegetable oil. They want to make SAF. They want to make methanol. So Irvine, ESB, GNI, Bord Gáis, Simply Blue, Port of Cork, UCC. This is our proposal that everything I've been talking about can happen. It can happen in the Lower Harbour. We can make ammonia. We can make methanol. There's the old gas fields. We can store hydrogen. The hydrogen can be brought ashore. There's 2 combined gas turbines down here that are about 1 megawatt. So if we make hydrogen, put it into the gas field, we have Dunkelflaute, no wind, hydrogen comes ashore. Mitsubishi are going for planning for an ammonia power plant. So if we make ammonia, there'll be a power plant that will make electricity from ammonia. So this is sort of future-proofing Cork for renewable hydrocarbons. So after we do all that easy stuff of offshore wind turbines and retrofit all our houses and buy electric cars, this is the next phase. That's me. It's my hour up. Is there anything else? Yeah. Yeah, so that's my presentation. I hope it was of interest.